Okay, so this is the robot container class. There is a lot in this class, and it does have the tendency to get a little bit long and a little bit out of control. So I'll share some techniques that we use to try to manage that. Um, Also, in this class. So in 3061 lib, there are uh, several subsystems, and some of those are really just to serve as examples. And we'll talk more about those example subsystems later, but they're the arm, elevator, manipulator, and shooter subsystems. None of them are going to work in any future robot we build or any past robot we've built or any robot that those of you from other teams build. But they're there to serve as examples and to highlight certain features and best practices that um, we've used over the years. Uh, so let's look at robot container. So as we saw, robot container is constructed inside of the robot class. Um, and so here is where we start to see some of the specific features of 3061 lib that make it useful for our team and perhaps your team as well. Um, The very first thing we need to do in robot container is invoke the create robot config method. And I'm going to jump to this right now um, because I want to explain what this does and why it needs to be done first. What this method does is it looks at which robot this code has been compiled against, and therefore it loads the appropriate robot specific configuration class. And so there are several different robots built into 3061 lib. You can have your default robot, practice robot. We have a competition robot, and then we base our simulation by default off of that one. It was called Calypso in 2025. That's why it's here. We have a little practice board that isn't a robot, but we use it to test certain devices. We have a vision test platform we use just for vision testing. And so that has a different type of robot. We've added support for XRP platform, and so that's a different type of config. So basically, this feature of 3061 lib, what it lets you do is you can have the same code base run on different robots. So our competition bot and our practice bot are not the same. And so we can have different configuration for those two robots. Certainly something like the practice board, the vision test platform, or an XRP is dramatically different than our competition robot. And this lets us to, again, use the same code base and features on different robots without having to um, have different projects and things like that. So it's important that this is called first, which is what we saw up here in the constructor for robot container, because other code throughout um, all of this code will be getting values from the robot config. And so therefore we need to make sure that we create that upfront and first. All right, so let's see what we have going on here. So the first thing we do in a robot container, this is standard Advantage Kit stuff, is if we're not replaying, then we'll decide, then we need to create all the various subsystems. If we are replaying, we'll jump down here first. We still create the subsystems, but you'll notice that we create them by creating an anonymous class based on the um, IO interface, so without any like hardware specific code in it. So think of these as just like stubbed out classes at that hardware abstraction layer. So we still create objects for all of the subsystems. They just don't have any hardware specific things if we're in replay, because all those values that would come from the hardware specific thing through those input classes are instead replayed based on the log file. But if we have a real robot and we're not in replay, um, then we create the different subsystems. So mm, we use CTRE subsystems for most of the things. There are some differences between when we create it for simulation and not. So we have two different cases here. Our practice board is again dramatically different. The vision test platform is dramatically different. The XRP is obviously different. So they have different methods here in terms of creating all those subsystems, and we'll see those momentarily. Um, Couple other things we do in the robot container when it's constructed: we disable all telemetry through live window. That just avoids that processing hit for something we don't take advantage of. We construct our field, and we'll see more about what that looks like later, but this allows some more advanced features in terms of pathfinding type stuff. We update our operator interface, and so that checks to see, okay, what joysticks, controllers, button panels, whatnot are connected, and make sure the buttons and triggers are mapped appropriately for those. Um, and then if tuning is on, we do set an alert to note that. We want to make sure that we don't accidentally go into a competition or something with tuning still enabled, as that's a significant performance hit as well. All right, so let's look at some of these. We're not going to look at all of these, but we'll look at some of these create subsystem methods. So here's one for CTRE. What you'll notice for each of these is that for all of the subsystems, including the drivetrain, we create the subsystem, like swerve drivetrain, arm, elevator, manipulator, shooter. And to each of the subsystems, we pass the hardware specific implementation of that IO interface. So here's the new Swerve drivetrain IO CTRE, so a CTRE based drivetrain. Here's Talon FX for elevators, which is what we usually use. But we'll see that that can be different as well. Vision requires a little bit of work. And so here's our first example of actually seeing us get the using the robot config instance and querying it for information. So here we're getting the names of all of the cameras on the specific robot on which this code is running. So different robots might have different named cameras and different number of cameras, and so this code would work regardless of that because it all comes from the config file. So we get all the list of the cameras, we create the corresponding Vision IO hardware specific objects for those. We do that because um, each camera needs its own Vision IO object. We load the April tag field layout and generate an alert if there's a problem with that for some reason. And then here you can see where we make new photon vision is the technology we use for our vision. So we create new Vision IO photon vision specific objects, again, the hardware specific implementation with the given camera name and the April tag layout. Build all those up into an array, and then we create our vision subsystem, which takes an array of Vision IO objects. So that's how vision works, and we'll have a whole video on vision later. The CTRE Sim one is pretty much the same. The biggest difference there is related to vision, because we don't create a Vision IO photon vision objects, we create Vision IO sim objects because we're simulating having cameras in a field. We don't actually have cameras. So that's the biggest change here. We don't have to do anything special for simulation of like CTRE related subsystems, as it supports simulation itself, which makes that quite a bit easier. For XRP, for example, you can see here that we only create an ARM, but we're creating an ARM IO XRP class, so that's a little bit different. We just create basically an empty vision. Oh, and we also create a differential drivetrain versus a swerve drivetrain because it's the XRP robot. So that's a change. We'll notice some code to handle the fact that there are significant differences between serve and differential drivetrains. And so you'll see a couple places in RobotContainer where we need to be aware of that. Our practice board, we basically stub out everything, and then based on what we're testing at the time, we can enable it. For example, we might hook up our practice board just to the elevator mounted on the workbench and want to be able to test that. So we could change this to elevator IO Talon FX, for example. I'm gonna fix this one in here. There we go. All right, vision test platform. The vision test platform allows us to basically run this code on a laptop and not have it connected to any robot. So in that way, it's a lot like simulation. But unlike running it in simulation, we do have real cameras. And so we want to actually create real Vision IO photon vision objects so that we can get those cameras and see all of that information. The vision test platform is helpful for verifying things on the field. You can just have a laptop and a camera and run the vision test platform as your robot and check your poses from where the camera is and see if, for example, like the field elements are in the right location and all of that is working as expected. Um, all right. Um, we'll talk more about Region 2D and Field 2D later. These are classes that are part of 3061 lib that allow you to do on-the-fly path planning from one region to another. Um, Path Planner these days has features similar to that, but this is something we've developed several years ago. And so we still use that from time to time. This is the method to check the operator interface and see if things have changed there. Um, if the operator interface has not changed, remember we check this like at the start of, or we check this while we're disabled. So if nothing's changed, we just return. If things have changed, we configure our button bindings again to make sure that we're mapping everything to the right buttons on the joysticks that are currently plugged into the driver station laptop. Configure button bindings. So this does all of the button mappings for commands. And this is where things can get like out of control. And so we've tried to do a little bit of a decomposition here to make this a little bit more manageable. We have a method that handles all of our drivetrain commands, another one that handles all of our vision commands. For each subsystem, we create a command factory singleton class with static methods. And we invoke the register commands method on that. So you can see an example of that for the arm subsystem and the elevator subsystem. In a real robot, every subsystem would have something like that most likely. Here is where we need to do things a little bit differently, whether it's a differential drivetrain or a swerve drivetrain. So you can see here where we use the robot config class to determine that because we invoke a different register commands method. One takes the differential drivetrain, one takes the swerve drivetrain in our cross subsystems command factory. So we have a command factory for each subsystem. For more sophisticated features that might use multiple subsystems at the same time, we put those commands in our cross subsystems command factory. Some commands we've kept in here. These are endgame alerts. This is another mechanical advantage feature that we've incorporated. This just gives the driver feedback when we're getting to the endgame period. So it's like a warning. And so this is done by changing the LEDs so that we know that, hey, it's time to think about whatever the end game is for that particular year. So that's what this is for here. Um, so, this is useful too. It's not that all triggers don't have to relate to buttons, right? So these triggers are based on timers and not based on buttons being pressed. And so that's certainly a possibility as well. All right, so here's that example of decomposition. So configure drivetrain commands. Again, it's done differently for differential and swerve drivetrains. We have an autonomous command factory, which handles all the autonomous commands. There can be a ton of those, so that's in its own class. And then we have a differential drivetrain and swerve drivetrain command factory classes as well. Here's our vision commands that are in its own method. We don't have a whole vision command factory, although I suppose we could. It's basically just to enable and disable vision support. And there's not much else in here. Check alliance color. This is where we're checking the alliance and we're seeing if it has changed, if we have it and if it has changed. And the field 2D class is responsible for keeping track of what our current alliance color is. So that is done here. I mentioned these methods, periodic, autonomous init, teleop init. I mentioned these in the context of looking at the robot class. These don't do anything in particular right now, but they're here in case a particular year warrants something being done in there. I guess with the exception of teleop init. In teleop init, we do call check alliance color again at the start of teleop. This is for an edge case where if the robot power cycles during a match, the first time that we would be guaranteed that the FMS's reported alliance color was accurate would be when the teleopponent method is called. So we do check it there, just to make sure we know if we're on the red or blue alliance. All right, that is the robot container class.